Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 148, Analyzing Generalization Across More Axes Than Just Accuracy or Loss, published on the 28th of April 2021 by Rohin Shah. Highlights: Distributional Generalization, a New Kind of Generalization, by Preetam Nakaran and Yamini Bansal, summarized by Rohin. Suppose you train a classifier to distinguish between CFAR-10 classes, except each airplane has a 30% chance of being mislabeled as a car. If you then train a model to achieve perfect accuracy on this badly labeled dataset, it will get 100% accuracy on the training set, and 97% of those labels will actually be correct, since 3% are mislabeled airplanes. Under the current paradigm, if we say that the model generalizes, that means that it will also get 97% accuracy at test time, according to the actually correct labels. However, this doesn't tell us anything about what mistakes are made at test time. Is it still the case that 30% of airplanes are mislabeled as cars, or does the model also make mistakes on, for example, deer? Distributional generalization aims to make claims about situations like these. The core idea is to make claims about the full distribution of classifier outputs, rather than just the single metric of test accuracy. Formally, we assume there is some distribution D from which we can sample pairs of points x, y, which generates both our train and test sets. Then the train, respectively test, distribution of classifier outputs is the pair x, f of x, with x coming from the train, respectively test, set. The train and test distributions of classifier outputs are the objects of study in distributional generalization. In particular, given a 0 to 1 valued function on distributions, called a test, capital T, we say that the classifier generalizes with respect to T if T outputs similar values on the train and test distribution. For example, given a distribution, the accuracy test checks how often the classifier's output is correct in expectation over that distribution. Generalization with respect to the accuracy test is equivalent to the canonical notion of generalization. Let's suppose that the classifier perfectly fits the training set, so that the train distribution of classifier outputs is the same as the original distribution D. Let's additionally suppose that the classifier generalizes with respect to the accuracy test, so that the classifier has perfect test accuracy. Then the test distribution of classifier outputs will also be the same as the original distribution D. That is, all distributions are identical, and there isn't much more to say. So the interesting situations are when one of the two assumptions is false, that is, when either 1, the classifier does not perfectly fit the training set, or 2, the classifier does not generalize with respect to accuracy. This paper primarily focuses on classifiers that do perfectly fit the training set, but don't generalize with respect to accuracy. One typical way to get this setting is to inject label noise, as in the mislabeled airplanes case, since this prevents the classifier from getting 100% test accuracy. Speaking of which, let's turn to our original example in which we add label noise by mislabeling 30% of airplanes as cars. Notice that, since the label noise is completely divorced from the classifier's input x, the best way for the classifier to minimize test loss would be to always predict the true CFAR-10 label, and then 3% of the time, the true distribution will say, "Lol joke, this airplane is actually a car." However, in practice, the classifiers will also label approximately 30% of airplanes as cars in the test set as well. This incurs higher loss, because the 30% of airplanes that the classifier labels as cars must be independent of the 30% of airplanes that the true distribution labels as cars, which implies that the model disagrees with the true distribution 4.2% of the time. This is worse than the 3% it would get if it consistently labeled airplanes as airplanes. Classifiers trained to interpolation are not Bayes optimal in the presence of label noise. Okay, let's get back to distributional generalization. We already know the classifier does not generalize with respect to accuracy. However, the fact that it still labels about 30% of airplanes as cars suggests a different kind of generalization. Recall that the train and test distributions of classifier outputs have the form x, f of x. Consider the feature L of x that says whether x is an airplane or not. Then if we replace x, f of x with L of x, f of x, then this now looks identical between the train and test distributions. Specifically, this distribution places 7% on yes airplane, airplane, 3% on yes airplane, car, and 10% on no airplane, C for every class C other than airplane. An alternative way of stating this is that the classifier generalizes with respect to all tests whose dependence on X factors through the feature L. In other words, the test can only depend on whether X is an airplane or not, and cannot depend on any other information about X. The authors make a more general version of this claim they call feature calibration. For every feature L that could be learned by the classifier generalizes with respect to all tests whose dependence on X factors through L. Note that they do not assume that the classifier actually learns L, just that if you hypothetically trained the classifier on a dataset of x, L of x, then it could learn that function near perfectly. They then provide evidence of this through a variety of experiments and one theorem. These are bullet points, but I'll number them because I don't know how to pronounce a bullet point. 1. If you plug in the constant feature L of x equals 0 into the conjecture, it implies that classifiers should get the right class balance, i.e. if you have class 1 twice as often as class 0, then you predict class 1 twice as often as class 0 at test time. They demonstrate this on a rebalanced version of CFAR10, even for classifiers that generalize poorly with respect to accuracy. When using a wide ResNet, for which the true CFAR10 labels are learnable, if you add a bunch of structured label noise into CFAR10, the test predictions reflect that same structure. 3. The same is true for decision trees applied to a molecular biology dataset. 4. A ResNet 50 trained to predict attractiveness on the Celeb-A dataset, which does not generalize with respect to accuracy, does satisfy feature calibration with respect to wearing lipstick, heavy makeup, blonde hair, male, and eyeglasses. Note that there is no label noise in this case. And 5. The nearest neighbor classifier provably satisfies feature calibration under relatively mild regularity conditions. In an appendix, they provide preliminary experiments suggesting this holds pointwise. In our mislabeled airplane example, for a specific airplane X from the test set, if you resample a training set, with the 30% mislabeling of airplanes, and retrain a classifier on that set, then there is a roughly 30% chance that that specific X will be misclassified as a car. The authors then introduce another distributional generalization property, agreement. Suppose we have two classifiers, F and G, trained on independently sampled training sets. The agreement conjecture states that the test accuracy of F is equal to the expected probability that F agrees with G on the test distribution. Loosely speaking, this is how often F and G make the same prediction for test inputs. The agreement property can also be framed as an instance of distributional generalization, though I won't go into the specific test here. The authors perform similar experiments as with feature calibration to demonstrate that the agreement property does seem to hold across a variety of possible classifiers. Interestingly, these properties are not closed under ensembling. In our mislabeled airplane example, every model will label 30% of airplanes as cars, but which airplanes are mislabeled is independent across models. As a result, the plurality voting used in ensembles reduces the misclassification rate to 22%, which means that you no longer satisfy feature calibration. Consistent with this, the authors observed that neural network ensembles, random forests, and k-nearest neighbors all did not satisfy feature calibration and tended to be closer to the Bayes optimal solution, i.e. getting closer to being robust to label noise in our example. Summary of the summary. Let's look at the specific ways in which classifiers make mistakes on the test distribution. This is called distributional generalization. The paper makes two conjectures within this frame. Feature calibration says that for any feature that a classifier could have learned, the distribution of its predictions conditioned on that feature will be the same at train and test time, including any mistakes it makes. Agreement says that the test accuracy of a classifier is equal to the probability that, on some randomly chosen test example, the classifier's prediction matches that of another classifier trained on a freshly generated training set. Interestingly, while these properties hold for a variety of ML models, they do not hold for ensembles because of the plurality voting mechanism. Section Technical AI Alignment. Subsection Agent Foundations. Link The Many Faces of Infra Beliefs by Diffractor, summarized by Rohin. When modeling an agent that acts in a world that contains it, see newsletter 31, there are different ways that we could represent what a hypothesis about the world should look like. We'll use infrabayesianism from newsletter 143 to allow us to have hypotheses over environments that are bigger than the agent, in the sense of containing the agent. In particular, hypotheses can vary along two axes. 1. First person versus third person. In a first-person perspective, the agent is central. In a third-person perspective, we take a bird's-eye view of the world, in which the agent is just one part. And 2. Static versus dynamic. In a dynamic perspective, the notion of time is explicitly present in the formalism. In a static perspective, we instead have beliefs directly about entire world histories. To get a tiny bit more concrete, let the world have states S, and the agent have actions A and observations O. The agent can implement policies pi. I will use delta x to denote a belief over x. This is a bit hand-wavy, but gets the right intuition, I think. Then the four views are: 1. First-person static. A hypothesis specifies how policies map to beliefs over observation action sequences, that is, a function from pi to delta of O times A star. 2. First-person dynamic. This is the typical POMDP framework, in which a hypothesis is a belief over initial states and transition dynamics, that is, delta S and a function from S times A to delta of O times S. 3. Third-person static. A hypothesis specifies a belief over world histories, that is, delta of S star. And 4. Third-person dynamic. A hypothesis specifies a belief over initial states and over the transition dynamics, that is, we have delta S and a function from S to delta S. Notice that despite having transitions, actions do not play a role here. Given a single reality, it's possible to move between these different views on reality, though in some cases this requires making assumptions on the starting view. For example, under regular Bayesianism, you can only move from third-person static to third-person dynamic if your belief over world histories, delta of S star, satisfies the Markov condition. Future states are conditionally independent of past states given the present state. If you want to make this move even when the Markov condition isn't satisfied, you have to expand your belief over initial states to be a belief over initial world histories. You can then define various flavors of acausal influence by saying which types of states S you allow. If a state little s consists of a policy little pi and a world history little o little a all star that is consistent with little pi, then the environment transitions can depend on your choice of little pi, leading to acausal influence. This is the sort of thing that would be needed to formalize Newcomb's problem. 2. In contrast, if a state little s consists only of an environment E that responds to actions but doesn't get to see the full policy, then the environment cannot depend on your policy, and there is only causal influence. You're implicitly claiming that Newcomb's problem cannot happen. 3. Finally, rather than have an environment E that, when combined with a policy little pi, generates the world history little o little a all star, you could have the state little s directly be the world history little o little a all star without including the policy little pi. This still precludes acausal influence. In normal Bayesianism, this would be equivalent to the previous case, since we could construct a belief over E that implies the given belief over little o little a all star. But in the case of infrabayesianism, it's not, for reasons I won't go into. Roughly speaking, the differences occur when you use a belief that isn't just a claim about reality, but also a claim about which parts of reality you care about. Since the existence of E isn't required, but we do still preclude policy-dependent influence, the authors call this setup pseudo-causal. In all three versions, you can define translations between the four different views, such that following any path of translations will always give you the same final output. That is, translating from A to B to C has the same result as A to D to C. This property can be used to define acausal, causal, and pseudo-causal as applied to belief functions in infrabayesianism. I'm not going to talk about what a belief function is, see the post for details. Subsection Forecasting. Link 3 Reasons to Expect Long AI Timelines by Matthew Barnett, summarized by Rohin. This post outlines and argues for 3 reasons to expect long AI timelines that the author expects are not taken into account in current forecasting efforts. 1. Technological deployment lag. Most technologies take decades between when they're first developed and when they become widely impactful. 2. Overestimating the generality of AI technology. Just as people in the 1950s and 1960s overestimated the impact of solving chess, it seems likely that current people are overestimating the impact of recent progress and how far it can scale in the future. And 3. Regulation will slow things down, as with nuclear energy, for example. You might argue that the first and third points don't matter, since what we care about is when AGI is developed, as opposed to when it becomes widely deployed. However, it seems that we continue to have the opportunity to intervene until the technology becomes widely impactful, and that seems to be the relevant quantity for decision-making. You could have some specific argument like the AI goes boom and very quickly achieves all of its goals, that then implies that the development time is the right thing to forecast, but none of these seem all that obvious. Rohin's opinion. I broadly agree that 1 and 3 don't seem to be discussed much during forecasting, despite being quite important. Though see, for example, value of the long tail, which is a link. I disagree with 2. While it's obviously possible that people are overestimating recent progress, or overconfident about how useful scaling will be, there has at least been a lot of thought put into that particular question. It seems like one of the central questions tackled by bioanchors from newsletter 121. See more discussion in this comment thread, and there's a link to a comment thread on the Alignment Forum post. Subsection Field Building. Link FAQ, Advice for AI Alignment Researchers by Rohin Shah, summarized by Rohin. I've written an FAQ answering a broad range of AI alignment questions that people entering the field tend to ask me. Since it's a meta post, i.e. about how to do alignment research rather than about alignment itself, I'm not going to summarize it here. Subsection Miscellaneous. Link Testing the Natural Abstraction Hypothesis, Project Intro, by John Wentworth, summarized by Rohin. We've previously seen some discussion about abstraction from newsletter 105, and some claims that there are natural abstractions, or that AI systems will tend to learn increasingly human-like abstractions, at least up to a point. See newsletters 72 and 80. To make this more crisp, given a system, let's consider the information, abstraction, of the system that is relevant for predicting parts of the world that are far away. Then, the natural abstraction hypothesis states that 1. This information is much lower dimensional than the system itself. 2. These low-dimensional summaries are exactly the high-level abstract objects/concepts typically used by humans. And 3. These abstractions are natural. That is, a wide variety of cognitive architectures will learn to use approximately the same concepts to reason about the world. For example, to predict the effect of a gas in a larger system, you typically just need to know its temperature, pressure, and volume, rather than the exact positions and velocities of each molecule of the gas. The natural abstraction hypothesis predicts that many cognitive architectures would all converge to using these concepts to reason about gases. If the natural abstraction hypothesis were true, it would make AI alignment dramatically simpler, as our AI systems would learn to use approximately the same concepts as us, which can help us both to aim our AI systems at the right goal, and to peer into our AI systems to figure out what exactly they're doing. So this new project aims to test whether the natural abstraction hypothesis is true. The first 2 claims will likely be tested empirically. We can build low-level simulations of interesting systems, and then compute what summary is useful for predicting its effects on faraway things. We can then ask how low-dimensional that summary is, to test 1, and whether it corresponds to human concepts, to test 2. A follow-up post, which is a link, illustrates this in the case of a linear Gaussian Bayesian network with randomly chosen graph structure. In this case, we take 2 regions of 110 nodes each that are far apart, and operationalize the relevant information between the 2 as the covariance matrix between the 2 regions. It turns out that this covariance matrix has about 3 to 10 dimensions, depending on exactly how you count, supporting claim 1. And in fact, if you now compare to another neighborhood, 2 of the 3 dimensions remain the same. Unfortunately, this doesn't give much evidence about 2, since humans don't have good concepts for parts of linear Gaussian Bayesian networks with randomly chosen graph structure. While 3 can also be tested empirically through simulation, we would hope that we can also prove theorems that state that nearly all cognitive architectures from some class of models would learn the same concepts in some appropriate types of environments. To quote the author, the holy grail of the project would be a system which provably learns all learnable abstractions in a fairly general class of environments and represents those abstractions in a legible way. In other words, it would be a standard tool for measuring abstractions. Stick it in some environment, and it finds the abstractions in that environment and presents a standard representation of them." End quote. Rohin's opinion. The notion of natural abstractions seems quite important to me. There are at least some weak versions of the hypothesis that seem obviously true. For example, if you ask GPT-3 some new type of question it's never seen before, you can predict pretty confidently that it's still going to respond with real words, rather than a string of random characters. This is effectively because you expect that GPT-3 has learned the natural abstraction of the words used in English, and that it uses this natural abstraction to drive its output, leaving aside the cases where it must produce output in some other language. The version of the natural abstraction hypothesis investigated here seems a lot stronger, and I'm excited to see how the project turns out. I expect the author will post several short updates over time. I probably won't cover each of these individually, and so if you want to follow it in real time, I recommend following it on the Alignment Forum. This concludes Alignment Newsletter number 148. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.